Bzz.
Your mom.
What to make of that. Welcome to Walkabout the Galaxy, the quirky astronomy podcast where the science is universal, the opinions are personal, and the music video is always 2 months away.
Oh, good.
We are Strange, Charm, and Down, the Astroquarks, also known as Josh Caldwell,
Addie Dove.
And Audrey Martin.
coming to you from the Walkabout studio at the University of Central Florida. Top Quark Jim Cooney is using stamps to play Scrabble while fishing.
He does that.
I don't know what that means, but
Yeah.
okay.
Well, you know what fishing is,
And I know what stamps are.
and you know what Scrabble is. So piece it together, Audrey.
Oh,
Put it all together.
My brain is too tired.
Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram, but not Mouth Shut,
What?
Dead Runners Society, or Film Flam.
Is this
Mouth shut?
Which
Is
one of
one of
those
them
did I?
that?
One of those I made up. You're
The second one.
Dead Runner Society,
Dead Runner Society?
sounds
Yeah.
wrong.
I think it's the first one.
You think I made up Mouth Shut?
Yeah.
And so
I think you made up Dead Runner
I
Society.
fooled you both.
Flim Flam.
Flim
There's a
Flam?
flim. Oh, there's a
Film-
Flim Flam, but now
I don't know. I made
think
up
there is a
Film
flim.
Flam. I thought it would be a cute,
do
funny
like
thing.
it.
It's like Film Flam, but it's about movies. So maybe I will create Film
You should make
Flam.
it.
Let's make
Grab
Film
that
Flam.
website.
Let's grab filmflam.com. For some reason, Mouth Shut and Dead Runner Society both exist.
Perfect.
Good.
You can contact us anytime at wtg@ucf.edu with questions, compliments, or suggestions for social networks. Our stumper today is another solar system power play.
Oh.
I'm having fun with, like, if you wanted to redesign the solar system,
I
how
like
would you
it
do it,
too.
right? So previously we talked about, like, if you could move the moon around or put some other moon here,
Mhm,
stuff like
right.
that. Yeah. So now we're going to move the Earth around.
Yeah.
But of course, we're just at the right spot in our own solar system. So for this one, we have to imagine that we could put the Earth around another star with a different mass and brightness,
Sure.
so that we would be at a comfortable temperature. You can choose your star,
Right.
so that you're at a comfortable temperature at an arbitrarily long year.
Okay.
Okay?
Mhm.
So your temperature is fine. The Earth is still going to rotate in 24 hours.
Mm-hmm.
Okay? So all that's the same.
Sure.
Still going to have your 23-degree tilt. So you're still going to have seasons.
Sure.
The
Love
same way, same magnitude, intensity of seasons. The question is, how long do you want the year to be? If you could just design your planet's solar system, how long do you want your year to be?
I think I would want my year to be maybe about 5 times as long.
Like
3 to 5.
3 to 5 years long? And
Yeah.
what's up with that?
So in Game of Thrones, there's like
Yeah.
super long seasons.
Winter is coming.
Winter's coming.
And it
Yeah.
took like 7 seasons for it to get there.
Yeah.
Yeah. Which was
And
like
that just
some
feels
number
like
of
too
years.
long. Yeah, exactly. It was just like, I don't know. I feel like some of the people in the show, like the characters were like born and then alive for a really long time and it was never winter.
Yes.
And that feels like it's too much. Like that's like, I don't know, 15, 20 years. Like
They may
that's
have
too
had
much.
maybe they had some weird obliquity things.
I think it
going
was
on,
more
too.
of a special, they
Or
probably
maybe an
had
orbital
some
eccentricity
weird orbital
or something.
eccentricity thing where
That's
like
probably what
sometimes
it
you had-
was.
Yeah.
But yeah, I think that's too long. But I still want to experience different seasons on a relatively quick
Okay.
rate.
Okay.
But
But a
I
little
want to
bit
have enough
more
time
time.
to like settle into it and like
Right.
really
Yeah.
enjoy it. So
Well,
I think
I can-
3 to 5, somewhere like 3
I
to
can
5
tell you, I
years.
haven't been in Florida
it have
very
to
long
be-
because the seasons in the season
That's
in
true.
Florida, summer, is already 3 to 5 times longer than it is everywhere else.
That is
so.
fair. I've been here for less than a year.
Yeah.
So we'll see how I feel.
That's a good point though. Does it have to be a circular orbit?
Yeah, same
Oh.
orbital shape. So, yeah,
Okay.
everything is just going to scale linearly with the length of your year. So, what do you want it to be, Addie?
In that case, I don't care.
Really?
So
You don't
interesting.
care? You're fine if your year was like 30 years long and summer would
No.
be 8 years or
I
something?
think to your point, Florida has just skewed my brain.
Yeah, there's no.
I think
It
I
could
would
be
like,
shorter,
I think I
too.
would like it to be, whatever it is, just like a nice precise place where all our numbers are easy. So maybe it's like 336 days long, so that it's exactly
You want
12
it to
months
have
of
it be
28 days.
exactly.
Okay.
Oh, okay. Well,
But maybe it varies slightly, like as the moon's orbit varies a little bit, the Earth's orbit varies a little bit too, so they're always synced up and your calendar is nice.
Okay.
But also, I don't know.
I wasn't thinking about that angle, but
The
that's a
years
cool
all
angle
just
to come
sort of
at it.
blend into each other, which is why.
Right.
But the years blend. But yeah, to the point of like the longer, shorter seasons.
If you made the year much longer,
Yeah.
then you could be like, well, let's see, when did I come here? I came to UCF.
In
it
the
was
summer.
the summer.
Yeah.
So,
I do kind of
Yeah.
like that.
places
Yeah.
it at this
But then
whole
you
thing.
need more of like a 10-year type.
Oh, that's
kind of
true.
scale.
But
But
then-
I think 5 years is nice.
But then also that puts the very kind of different rhythm on your lifetime.
It does.
You know, it's like, this could be my last winter.
You could
know?
live on an Earth where, like, we have the phrases like, right when you're born, it's spring,
Right.
and then you have summer,
I was
and then
kind of
fall.
hoping
So
somebody
you
would
could have
say,
like a 100-year orbit,
yeah,
and then it would be those things.
that would be your life.
It would suck though if you were born in the fall, and then like,
Yeah.
it wouldn't suck. I mean, it would just throw off all the analogies.
Yeah.
Though.
It would change everybody's whole sort of like people who are into astrology and that kind of thing.
Oh,
It's
yeah.
like,
Oh, yeah.
you were born in
the spring.
You're a spring person or
Yeah.
you're a summer person.
I actually
or
think
something
that
like
would have a bigger effect, though, right? Because like
It
seasonal,
would,
Oh,
because
yeah.
your
seasonal,
development,
also seasonal
affective disorder.
affective disorder, like it's a
Oh,
significant thing, right?
true.
So like if you're born and in winter and it's dark for your
the
developmental,
first 20 years of
yeah.
your life,
Yeah.
it's cold and dark and depressing.
you might be a very different
You might be a
person than the
different
people
person.
who were born in the summer.
Definitely.
Yeah.
That
But
has
you
like
still-
whole
but-
generational
Oh.
implications.
Yeah. So, and then people can't really like, they're kind of,
Change.
right, so your fall parents
Oh
are
yeah.
going to be having winter babies,
Mm-hmm.
right? Because they're going to be
Oh,
in
that's
their
true.
Yeah,
childbearing
That's true.
age
Yeah.
in the winter.
They'll either
So
have
that's
fall,
also going to
be fall, or like late fall to early winter babies.
right.
Yep.
So that's also going to be affecting what kind of person is coming. As their parents are going to be a certain kind of person and so forth. It could be really interesting.
I like it.
Well, today we're going to talk about none of that.
Perfect.
An explanation for the interstellar interloper Oumuamua, and a new way to learn about dark matter. But first, this episode of Walkabout the Galaxy is brought to you by Dirac cones.
Excuse you?
For cool refreshment and to describe the electronic band structure of graphene and topological insulators, try a Dirac cone. Always available at 2 for the price of 1, Dirac cones cool you down while describing your 2-dimensional materials. Act now for a special deal to upgrade your 3-dimensional Dirac cones to hyper cones for your Dirac
Oh.
semi-metals. Dirac cones, seize the yay.
Oh, I hate it.
Yeezys. Just kidding.
Government.
Yeezy,
Yeezy.
Yeezy shoes. Or something.
Yeah. Seize the Yay.
Seize the yay.
Some sort of yoga company.
Capri Sun.
Ooh, that's fun too.
Capri Sun.
Yeah.
Cones is your Dirac cones. is
Oh,
your
what are
clue.
those? What are those ones? The like ice cream cones that are dipped in chocolate and then they have like peanuts on top of
I
them.
don't know.
Drumsticks?
Yeah, drumsticks. Drumsticks?
No,
No.
because this is a new. Well, unless Drumstick like rebranded, because that's got to be a newish
Seize the yay.
motto.
Seize the yay.
Yeah.
It is, I think, newish,
Yeah.
and it's one I had never heard of because this company has a much more well-known slogan,
Phrases.
which is 31 flavors.
Baskin
Baskin
Robbins.
Robbins.
Oh, interesting. So
Baskin
you were on
Robbins
the
is
right
trying
track.
to
Good
get-
job.
Trying to get the seize
I
the
was?
yay out
With
there.
drumsticks.
Oh, that's okay. What? I was thinking Yeezys or not.
No.
Ice creams.
I feel like our sponsor has been attending colloquia at UCF recently.
It's quite possible. It's
There's been
quite
a lot
possible.
of interesting talks here for
I clearly
faculty positions.
have not been attending colloquia.
Yeah, we've had lots of them.
We're having
Although I am very
Lots of
excited about
bonus ones.
hypercones.
oh yeah,
Ooh.
Are those the
I
ones that
don't
have
know what
caffeine
means.
in
they're
them?
multidimensional.
Do they have caffeine in them?
Well, they're all multidimensional, but these are extra dimensional.
Okay.
Relativity.
They launched.
They launched their thing.
It was
They're
blue.
Finally.
It was
yeah,
blue.
so it's pretty cool. It's pretty exciting.
It was blue?
So it's a different.
What?
It's a methane.
Methane,
and the
liquid natural gas
yeah,
fuel.
and it looks blue when it burns.
Yeah.
And
So
it was really cool. The images they got that like show the mock cones and the different
Yeah.
engines. Oh, they're super cool.
Most rockets are going up. I guess SpaceX is rocket fuel, basically kerosene.
Hydrazine? No, they're not hydrazine, are they?
It's kerosene, isn't it?
Oh, maybe. Okay.
Yeah,
One
rocket
of them's
grade
hydrazine.
kerosene. I thought. In any event, it gives a more orangey flame, and Relativities, which is the 3D printed rocket.
Yes.
And this one didn't have any
Paying
payloads,
customers.
no paying customers, so it was a test flight. And it was, I'm sure they checked off many things on their milestones
I
and
think
accomplishments
Starship is
list.
going to use methane.
Mm.
Okay, and I think
Sorry to go back to that.
I think is the BE4 Blue
That's a
Origin.
good question.
But in any event, their second stage they had an anomaly. So the first stage looked like it was a nominal flight, and they had 9. I think.
BE4 also uses LNG.
Liquefied natural gas,
Yeah.
same as this one. Yeah. So pretty exciting. It was pretty cool. It was a smaller rocket, so from our vantage point here in Orlando, we can see these things. And it was
Little
a
dot.
noticeably
It was a smaller
tinier
dot,
little flame
but it
than
was
we
bluer.
usually see. But it was also noticeably
It's
bluer.
very exciting.
Yeah.
Yeah.
So that was cool.
very
3D
pretty.
printed
They
rocket.
made it through. So the second
Max
stage didn't work,
Q.
but they made it through Max Q, which is where there's the most pressure on the rocket and where things could more likely crumble, for instance.
Right.
And it made it through that. So that's a great
Combination
sign.
of the
good.
acceleration of the rocket and the aerodynamic stresses on it.
They were pretty. They
Wow.
seemed to be pretty happy
Yeah.
with the performance. So it's just, and the second stage lit initially.
Yeah.
And then you were like, oh
It's
yeah,
like-
that's not doing
It's
anything.
sort of petering
Aw.
out.
Yeah.
It's like,
Yeah.
yeah.
Hmm.
Exciting.
Yeah. Let's see. Nuclear reactors.
Oh yeah. Talking about other fuel sources.
Yes.
On the moon. So there's the recently announced Rolls-Royce. When we
Right.
think about the moon,
How?
we often think about Rolls-Royce. Has announced that they're working on a little micro-reactor to develop nuclear technology for the moon. And this is going to be funded by the UK Space Agency to do some
Interesting.
actual development of a little nuclear reactor. So there's been groups talking about nuclear reactor for the moon for a long time.
So usually I think about putting solar panels on the moon
Sure.
because there's no weather, right? I mean,
Sure.
one of the
There's
knocks about
space weather.
one
There's
about
space weather.
the knocks of solar panels on the Earth is it's cloudy and it's night, and on the moon you can even get some really long duration
Yeah,
exposure
totally.
to the sun, and you don't have to worry about clouds or rain or anything like that. You potentially have to worry about dust blasting and things like that if it's near your rocket landing site. So why do you think they want to even be exploring?
I mean, a lot of the challenge is unless you're at the South Pole, you don't have and this goes back to our conversation about like lengths of time, right?
Get long nights.
You get really long nights, right? It's
Yeah.
14 days and
yeah.
14 nights.
Right.
14 of your
14
sunlit
Earth days.
of your sunlit Earth
Yeah.
days. So 14
Oh my
14
goodness.
Earth days are sunshine on the moon, and 14 Earth days are then nighttime on the moon.
And then you would have no power coming
And then
in,
you'd have
right?
no power, right?
Right.
So like any of our equatorial landing sites, anything that's not South Pole, where we have some of these PSRs or
Permanently
PIRs, permanently illuminated regions,
Uh-huh.
you're not going to have continuous solar power. So you need
True.
batteries, or you need. This is a big
Interesting.
thing with all of our like rovers and missions we've sent. We
Right.
have sent, and we're talking about sending, is all the first ones are just expected to be about 10-day missions because they're not
Right.
expected to survive the night because it gets real cold.
Right. Not only do you not have power, it gets very cold, so then you
If
would
you
want
had
to use
power.
some power to heat things up.
Yeah.
Right. And so, yeah.
So nuclear is a good solution. Also, like on places like the moon, you could put your nuclear reactor probably pretty far away from you,
Uh-huh.
and then
Run some
run
cables.
some cables over to
nice.
you. And
Yeah.
so there's ideas for how you could take care of that.
Yeah.
Is this nuclear reactor different in any way from ones that were like
Well, what's
more
your number
familiar
one
with?
concern with nuclear reactors, Audrey?
mine?
To put you on the spot.
My number one
What
concern.
should everyone's
Yes.
number one concern be with a nuclear reactor?
Spent fuel rods.
Actually, that's a good
that's
one,
a good one.
but not the one I was thinking
Oh,
of. But that is a good. That probably should be what I was thinking of, but
Well-
it wasn't.
I guess nuclear reactors
Go boom.
on Earth, it heats up. It makes
Yeah.
steam, and so there's no.
You need to cool.
You need a lot
to
of
keep
water.
them cool. And you need to keep the reaction not from running away.
Right.
And so you got to keep the reactor under control and cooled.
Yeah.
So you have to dump your excess heat somehow. You don't have an atmosphere to do that, or lakes and rivers, which, if you've noticed, nuclear reactors are always next to like an ocean or a giant body of water, so you can like bring water in to cool things off. So I'm guessing that that's kind of what the design differences are. I'm just speculating that
so
they need to make sure that it can operate in those weird thermal environments of the moon.
Kind of cool. That could mean cool stuff for nuclear reactors on
Anywhere.
Earth.
Yeah, so Rolls-Royce is actually, this part of the company is actually a very different company than the cars.
I was going to ask if this is like the first thing, or like the first nuclear reactor that Rolls-Royce has made.
They have a small modular reactor program, says their website. But I don't think they've actually made any yet, but I think they're developing them for Earth, but they're also like, well, we might as well try it for the moon too, right?
That's awesome.
But it is different than the car company, which is owned by BMW now, technically. So.
Oh.
Yeah.
Well, that's
So it's a separate company with the
I think
same...
so.
Interesting. Because they also are well known for making jet engines.
Yeah. A lot of the car companies had roots in jets.
Oh.
Several of them have.
Interesting.
Yeah.
I didn't know that.
But Rolls-Royce, they have a bunch of... this version of the company, I think, is the jets and the power systems and aviation and defense and stuff like
so
that.
the automobile brand has just been sold off.
Yeah.
Okay. So that'll be interesting to see how that develops. And it's a good point that the sunlight is free and abundant, but the nighttime difference is a lot worse between the Earth and the Moon on the Moon than the weather is better, but the length of the night is worse.
Yeah.
And then we had the rollout of the Axiom spacesuits.
For
the Artemis.
Next generation spacesuits.
For
Did you know what they did at this time? They designed some for women.
oh.
Crazy.
Why? Just kidding.
How are those different than the ones for men, Addie?
Shapes.
Different shapes?
Different shapes. They probably have a nice... No, I don't know. I've been watching a lot of stupid, like, superhero things where they always have, like,
Some
a special
nice
breastplate and
hourglass
different, like, figure stuff. It's like, no, it's none of that. But like, so actually most of... a lot of the problem with current astronauts in spacesuits is like the women are just smaller than a lot of the men, and so the suits, even the smallest suit they designed, doesn't always fit the women. Although I was told I would be able to fit in one of the spacesuits quite fine because I'm as tall, if not taller, than several astronauts.
Yeah.
So.
So you're all set.
But it's also
they're
really hard. They're really the
More
current
hard
ones
shell.
are very hard to move around in. Like you have to be really strong to move the actual physical parts of the suit. And the new designs in general are just sort of more flexible, I think.
So this is part of one of the many differences between the Apollo project and Artemis is NASA's doing more sort of outsourcing things to companies. It's not like companies weren't involved in all these things in the Apollo days, but now they have sort of more authority.
Yes.
And they're like, NASA says, here are requirements, you company go meet them and we'll stay out of your way, and then you deliver a product. And one thing I found curious reading about this, so this spacesuit, is that the company is not actually selling the spacesuits to NASA, they're renting them to them or something like that.
Oh, interesting.
So that the spacesuits don't belong to NASA, the ones that the Artemis astronauts will be using. And from what I understand, initially they're not even planning to return them because it's mass.
Oh,
and
they're
they
just
would
gonna leave them
rather
on the
bring
surface?
moon rocks.
Oh, I'm on board for that.
Than the spacesuits. So the spacesuits will be left behind.
Does
but I
that
read
mean-
something that's like, but anyway, if NASA did bring the spacesuits back, we would still own them because we're providing them a service. I'm like, I
seems
actually thought
strange.
you were providing them a product.
Yeah.
Like,
So does that mean
the service is here? It's like if I go to
Right.
Burger King, I'm like, I'm not ordering a service.
You're renting a
I'm
burger.
ordering a burger.
Now I'm hungry.
Does-
An
So-
impossible,
Except not
an
from
impossible
Burger King.
burger.
But does that mean that
Specify.
if the spacesuits are left, like if they're not brought back, then NASA's just kind of continuously renting them because
I
they haven't been returned?
I don't understand the whole thing about this as a service didn't make any sense to me because it's actually not a service. The company isn't. Here's the thing. It's like we actually
Yeah.
need a thing. We need this spacesuit.
That's so strange.
But they, you're talking about the difficulty of moving around in spacesuits because they have to be pressurized. So it's a big, you're inside a big pressurized gas bag surrounded by a vacuum. So you have this pressure differential between inside and outside, and that intrinsically makes it difficult to move around. So it's a non-trivial job to make a good spacesuit.
Yeah, I mean, I think, so to one point about, like, leaving it there, especially with this first mission, the architecture of Artemis 3 is going to be very, very different than the architecture of subsequent missions. And part of that is less long-term, sustainable reusability stuff and more just like, all right, can we do this again?
Right, yeah. We did it 55 years
that's
ago.
fair.
Can we do it again?
Because I think long-term, there's a lot of designs where the spacesuits sort of dock with whatever roving vehicle you're in and other things. And so there are different long-term designs that will need to be modified and maybe do get left. Like we leave spacesuits up on station sometimes, right? So like there is some give
So
and
one
take
of the
with that.
differences between this one, I think functionally the most noticeable one to me anyway, is that it's not like put on a pair of pants and then put on a spacesuit jacket and then seal it up at the waist. You climb into the suit through the backpack.
Right.
Yeah.
So the backpack has this hard, kind of like a hard shell suitcase, right? And you sort of open up a door and then you slip in to that from the rear, and then somebody shuts the door on the back and that latches shut. And because some of the Apollo and even space station and shuttle era had like difficulty. The whole suiting up process was like a kind of a nightmare.
Yeah.
And on the moon, after EVAs on the lunar surface, they had particular difficulty because of the moon dust that
all
was
those
like,
seals and everything.
all those seals
Get dust in them.
jamming things up. So that's pretty cool.
Yeah.
Yeah.
And I will say, like, so this is they were specifically selected for Artemis 3. There's another company, there's at least one other company that's competing in general in designing suits that has been funded through some initial contracts.
Okay.
And there might be others in the future. So that's one of the cool things about the way NASA's doing these commercial contracts is they often fund several companies to sort of do the initial phase and then they down select to one for certain missions, just like they have for the landers and for those stuff. But that doesn't mean that other companies can't then come on board and provide them for Artemis 4.
Right.
5, 6, 10.
Right.
Cool.
Yeah.
Okay, so I'm going to actually drop the trivia on you because it's sort of more closely related to what we've just been talking about than it will be to our next two
Can I really quickly
science topics. But
just add that Kathy Loiters, who's been the administrator on the HEO, the human spaceflight side of things for several years now, has announced that she's retiring from NASA and will be stepping down. So that's she's the first woman in that position.
Wow.
And she's been really good over the sort of big turbulent big exciting change time. So we'll see what happens. That's all.
Are you applying for her position?
I am not. I
Okay.
don't think I'm qualified for that position.
Doesn't hurt to apply.
Sure.
What is the most massive? It was the relativity rocket launch that was making me think about this, and it's like all these different rockets have different sort of payload capacities and things like that.
Oh, yeah.
And I was also thinking that this would be a fun question to torment Jim with because it's his
Instead we'll torment
his least
Yeah.
favorite
No,
type of question.
I'll be tormented.
What's the most massive single object that has been sent into low Earth orbit?
Oh,
So, the most massive object in low Earth orbit is the International Space Station, but that was launched
in bits
multiple
and pieces.
launches put together up there. I'm talking about like you have one launch, you carry one thing up there. Is it Hubble Space Telescope? Is it
Your mom.
a Starlink satellite? Is it? and what is it? Follow up, of course. What is the most massive spacecraft that's been an interplanetary spacecraft? Maybe not.
Okay.
Maybe not.
Who
We'll find out.
knows these things?
Somebody. The internet
People who
knows.
know
Oy, oy,
trivial
oy.
things.
That's true.
Yeah. Okay, so let's talk about Oumuamua.
Let's.
Oumuamua. If people remember, 2017 is when it was.
Has it been that long?
It's been that
Yes.
long. It was discovered.
Oumuamua.
Yeah,
I know.
it was our first interstellar visitor object. And fun fact, I had it written somewhere, but Oumuamua, the name, it means like first visitor from afar.
Yeah. In
which
Hawaiian.
which is pretty cool.
It's a fun name.
Yeah, so Oumuamua came in to the solar system pretty fast.
Screaming through.
Just screaming through.
Too fast to be a homegrown
Yep.
I
comet.
think 3 times as fast as your average comet. And it popped onto the scene, and people were like, WTF, what is that? And as it got closer and closer to the sun, it kind of started to speed up.
Mm-hmm.
Which was surprising to a lot of scientists because
Well, in the wrong direction.
in the wrong direction, but also this happens with comets. Like that,
Yeah.
it speeding up wasn't a big deal, but comets have tails,
Mm-hmm.
and Oumuamua did not have an observable tail.
Right.
Sure.
Yeah, so
And the comets have tails because when they get close to the sun, they outgas gases and dust
Mm-hmm.
and
famously,
stuff
yeah,
that we can see.
which is kind of
That
like
gets
what a rocket engine
illuminated.
does.
It is, yeah.
Just like
You
a
know,
rocket
blast
engine.
stuff off one way, the thing goes the other way.
Yeah.
So it
So
can
the
change
comet
its
blasts some
trajectory.
stuff off one way, it'll go the other way.
Mhm.
Yeah, they call these the comet scientists call this non-gravitational forces. So it's not they're moving, they're accelerating in a way that's due to force other than the gravity of the sun and the planets
Yeah.
acting on it.
Yeah.
And the whole comet itself, even Oumuamua, is too big to really be pushed around significantly by radiation pressure, which would be
Right.
another non-gravitational force.
Yeah.
So it had even been suggested that this acceleration of Oumuamua was due to
Alien.
Aliens.
Yeah,
So-
we've covered this a few times
Yes.
over the years since 2017.
Mm.
And there was a famous outcome that was like, oh, it's probably an alien spaceship.
yeah.
It does have a really weird shape,
people.
Yeah, it's
but
kind
we
of
also don't know the shape that well because we have so few observations.
Right.
of it.
yeah. It's like somewhere between a cigar and a pancake,
maybe. Yeah.
or something.
Or something.
yeah.
So now
And so we
there's
did not only with comet tails, usually it's a visible spectrum, a visible thing that you can see, but also you can take spectrum, and we were able to take spectra, very small amount of spectra of the object to look for like gases, and we didn't see anything.
Right.
So
Exactly.
it was hard to explain that it was some sort of comet tail.
right.
But
But so now there's been new modeling that proposes. So this idea had been floated as one of many possible explanations
Right.
for the unusual acceleration of Oumuamua, and that has now been studied and modeled in a way that seems to say that's probably what was going on.
Yeah,
And what is
in a very, very simple explanation.
so simple.
Okay.
Well, so yeah,
It's
I
simple
would
in
consider
the
it.
It's simple in the headline
In the
level,
se-
but in the
I think it
details
is.
it's pretty kind of complicated.
So-
It's simple in that it doesn't require alien technology.
That's true.
Or a large block of like
Oh.
straight up hydrogen ice.
Right,
Which
right.
is so basically what could give rise to the acceleration is outgassing of H2. Because we wouldn't see it in the visible, we wouldn't see spectra of it, so it has to be something, and
This is molecular hydrogen.
molecular hydrogen.
Which is like famously doesn't want to be an ice or a liquid
Exactly.
or anything except a gas.
And it also doesn't want to
Exactly.
be detected.
It doesn't want to be detected. It's
With
just like,
spectra.
leave me alone, please. And yeah, and so scientists at first were like, well, I guess, I don't know, like, is it just like a block of like molecular hydrogen? Probably not, but I guess it
That
could
could
be.
work.
It
It
could
could
work,
work, yeah.
but that doesn't really make sense.
Right.
If you think about it. And so some researchers thought about it a little harder and and figured out that if you have just your regular old comet-like composition, and then you expose it to cosmic radiation for a long amount of time, you're going to get space weathering that results in molecular hydrogen and then gets trapped within the ice. And so
that is that like actual, is the space weathering implanting hydrogen into
I don't know.
sort of molecular structure of things?
I don't think so. I think
or
it's
is it changing the molecular structure of
it's
what's there and rearranging it so that you end up with some H2 molecules inside one of my favorite words, clathrate.
So it's related to clathrates. This is something we've been talking about actually in the ICES and solar system seminar a bunch, because like there's a bunch of outer solar system stuff and observations where we detect some like carbon and CO2 and stuff like that, and CO, and we detect them further in than we expect to, and it must be because they're trapped in like lattices and cages of water ice and things like that. And so I don't think it's necessarily even making it right now through the irradiation. It might just already have been in there.
Yeah.
So it's both trapped and maybe it's making some and stuff like that. But it is trapped in a clathrate like lattice structure.
That's a first-class clathrate.
Yep.
So those are, as you described, molecular cages. So you would have, so then when it comes close to the sun, those cages break open.
Yeah.
And then the H2 comes out like exhaust from a rocket engine.
Yep, you got it. And that's, a very simple, straightforward explanation.
Right. And so what they did was they were like able to crunch the numbers.
They modeled it and they said, yeah, that could do it.
We can put enough hydrogen in there that's a sensible amount, and it would come out at a sensible rate, and it would produce the observed accelerations. That's cool.
Yeah.
Science at work.
It's just, it's just a very nice, concise story.
And it's cool too because one of the lead author on the paper actually isn't like a planetary scientist necessarily. She's a person who does like H2 and ice stuff, and like saw a talk from a person who like is a planetary scientist that had a theory, and they like worked together.
Good for them.
And it was a cool.
That's awesome.
Yeah. I actually met her at a JWST workshop, and she's
I bet
very
she's
nice.
super interested in all the JW stuff.
Well, we were at a workshop for it, so yeah.
Oh, cool.
That's fun.
The lead author or the planetary science author?
Jenny.
Lead author, yeah.
Okay, cool. Yeah. Well, in a very, very different realm, our other story has to do with dark matter and black holes. So Jim picked a lousy episode to be playing Scrabble with stamps while fishing.
Seriously.
He's missing some of
still
his
don't
favorite
get it.
things.
Those are the things he does.
But how do you play Scrabble with stamps?
Well,
He's
instead of
on
putting
a
down a letter
boat.
tile, you put down a stamp.
But how do you play Scrabble?
You're thinking way too hard about
This
this.
doesn't make any sense.
You're thinking way too hard about
I'm
it.
not sure if you belong on this show.
I don't know if it's going to make sense.
It's been great, guys.
So, dark matter. Oh, well, one thing I want to say about the dark matter is that
Just about the dark matter.
when you hear dark matter, you think material that's actually, you think about physically dark material, like charcoal or something.
Yeah.
Right?
But that's not what
But that's not what it is at
No.
all, because that charcoal, dark matter, asphalt, does actually interact very strongly with light.
That's why we see
It
it.
absorbs it,
Yeah.
and so we see it blocking that light or not reflecting it.
Yeah.
And so dark matter,
Dark matter you
is
can't really conceptualize.
famously dark because it doesn't interact with electromagnetic radiation.
Yeah.
What it does do is interact with things gravitationally. So that's how we know it's there. We see things moving around in ways that we can only explain by putting some extra mass there that we do not otherwise see.
Yeah. It's really a placeholder name
Yeah.
until we figure out what it is.
Yeah.
I mean,
But it's probably something with mass.
Yes.
So
Because it makes gravitational effects, so it has mass.
It's closer to
The one thing we know
describing
about
what it really is than dark energy is to describing what it is, I think.
Yeah.
But in any event, so gravity likes to bring masses together. So you got dark matter in the universe, you've got black holes, which are famously massive. And so if you imagine your galaxy is permeated with dark matter, and there are black holes in your galaxy, that you would have some, in addition to having gas and stars and other things like that around your black hole, you would also have an accumulation of dark matter. And modeling had suggested that because the dark matter doesn't interact with radiation the same way that regular matter does. It has a different dynamical story in the vicinity of a black hole.
Yeah.
And the predictions say that that would produce a very steep density profile of the dark matter around a black hole, different than the profile of the regular matter.
Okay.
Okay, so you have two different sorts of distributions of matter, and
Sure.
the
And distributions
dark
of matter.
matter,
And speeds. And speeds are how we originally
right, found this stuff in the first
dark
place.
matter in the first place. It was like,
Yeah.
these things aren't moving the right way.
So there were these models that, okay, you would have these density spikes of dark matter, and but they'd never been observed. And if dark matter behaved a certain way, maybe it would produce some emissions of gamma rays or things like that. But now, in a paper by Chan and Lee in the Astrophysical Journal, Letters, they have found two nearby stellar mass black holes.
How nearby? Should we warn Brendan?
Yes.
Okay.
That seem to show that their companion stars are spiraling in to the black holes faster than they should if there weren't dark matter.
Oh,
Or to put it another
no.
way, their spiraling in can be explained, their abnormally fast orbital decay can be explained by the presence of this steep dark matter-ish density spike around the black hole.
So we
kind
have
of-
observations of these stars that are orbiting a black hole, and we can see how fast they're moving,
right.
and we can see that they're changing how fast they're moving and where they are in their orbit.
Yeah, so you measure, like if you're spiraling in, the next
often
time you
am.
go around, it takes less time than the previous time.
Yeah.
And
yeah.
so that's what they've been able to measure is the change in
And
the
these are big
period.
measurements? These are big changes in period?
No.
Like DART, we changed its period pretty
Right,
significantly,
by
right?
20 seconds or
by
something
20
like
seconds?
that.
Is this similar to that?
These are something like, I believe, 1 millisecond per year
What?
Okay.
change in the orbit period
Yeah. Yeah.
of these
So really
stars
obvious.
Oh my
orbiting.
God.
And the prediction without dark matter is that it would only be 0.02 milliseconds per year. So
Yeah.
it's something like 50 times bigger effect than. So yeah, there's an effect there that has to be explained.
So it's really tiny, but it's bigger than we expected.
So does that mean
No
there's
comment.
even more dark matter?
No, I mean,
No.
the expectation is what
That
would it
there's
be
no
if
dark
there's
with,
no dark matter?
With the dark matter, it makes sense.
So
Yes.
with the dark matter, you can get to this 1 millisecond per year decay of the thing through a process called dynamical friction.
Oh, you love talking about dynamical
I
friction.
do love talking about dynamical friction, which is if you imagine one object sort of moving through a swarm of other
I
objects.
imagine that a lot.
Bees.
It's like when if you're in a crowd
Mm-hmm.
and you really got to get
bees.
somewhere in a hurry and
You're trying to
everybody
run
else.
away from the bees.
Yeah, because of all the bees.
I'm thinking like you're in the mall.
Sure. But not Fashion Square Mall.
For bees.
Okay, some other mall. You're in a mall and you're on a mission to get to a store and everybody
Honey
else
store.
is just milling around.
Sure.
So
They
as
don't
you
need honey, they're
move
bees.
through, your gravity attracts those other shoppers towards you. But because you're moving quickly, they sort of tend to pile up behind you.
Because you're wearing a floral shirt.
Yeah.
You guys are making this really hard. You're
Maybe it's
moving
mosquitoes.
along.
That's a good analogy
All those
for it.
shoppers are drifting around. They're attracted to you by your gravity, but because you're moving along, they trail behind you.
Maybe
And
you have
so
a soft pretzel.
Then
that's why
there's
they're trailing
more
behind
of
you.
them behind you than there are in front of you,
Okay.
and the collective pull of all of those shoppers behind you slows you down. That's friction.
Okay.
Okay.
All right.
But
So put a
Oh, that's
planetesimal
interesting because
moving through a rapid swarm, moving rapidly through a swarm,
yeah.
then those things will tend to collect behind it, and then there's an asymmetry in the gravitational pull of the swarm. More stuff behind you than in front of you, so that slows you down. So that's what's
interesting,
going on in this
because
disk.
like in a different analogy, in a different thing where you have
So
a
you got
wake.
bees or shoppers.
No, neither.
getting stung
Neither.
more from behind than in
Yeah.
front.
Yeah, but like right when you're biking, or driving a car.
That's right.
When you are driving quickly, there's a wake behind you.
Right.
And it's often advantageous for the other person to sort of
get
go
in
in
that.
there because there's reduced drag on them.
That's right.
But this is a different case where you're piling, there's a bunch of bikers now biking behind you and they're slowing you down.
From their gravity.
From their gravity.
That's right.
Wow.
Fat
Yeah.
bikers.
I know.
So, yeah, we
PHAT.
could think about the yes. Anyway,
Cool.
you get the idea. If
I think we do.
If you're moving through a swarm
Bees.
more quickly than that swarm of stuff,
Sure.
that swarm will
They're like,
collect
hey,
behind
don't
you,
go so fast.
and its gravity will pull you
Yep.
back and slow you down, and therefore cause you to lose energy and spiral into the black hole.
Oh,
So-
why are bees making
No.
us spiral into the black
So
hole?
the dark matter around the black hole, they modeled the effects, the gravitational effects of that dark matter distribution, which is different than the ordinary matter distribution because the dark matter doesn't interact with light, and therefore has a different pileup behind the star and pulls on it more, causing it to spiral into the black hole faster than it otherwise would. And ta-da, it's a completely new way of seeing dark matter on a much smaller spatial scale than we've seen
interesting.
before.
Which is a pretty cool result. I will say, all of that is like, I was reading this paper and I was like, oh, there's going to be a cool figure.
Yeah.
There was like one figure with 2 red and black lines.
No. Yeah, I want to see
But I want to
the
see the
density
little density distribution.
Yes, the
I
figure
wanna see-
is underwhelming.
Does it help kind of define the distribution, this
It
discovery?
does.
Well, I mean, it helps you understand how dark matter
Behaves a little bit more.
Okay.
right? Because,
Because it
is
does constrain where that density distribution needs to be in order to create this decay rate a little
Right,
bit,
okay.
which, ties back to.
And some of the previous models had said, well, if you have dark matter piling up around a black hole, you might see gamma rays coming from that because there could be certain types of dark matter could self-annihilate and emit gamma rays, and we haven't seen that.
Okay.
So now we have
we're getting
seen
real
evidence for
complicated now.
the spike,
Okay.
but not that gamma. So it helps narrow down this question: what the heck is dark matter?
Also, it has cool terms like dark matter density spike theory and the spike index,
That is
which
pretty
is
cool.
pretty awesome.
I should maybe see if they want to sponsor an episode.
Yeah,
All right.
the spike index.
So, wait, one more question.
Sure.
Okay.
This was the decay of 2 stars.
It's 2 separate systems they see.
Oh, 2 separate systems.
Yeah.
Yeah.
Okay, this isn't one black hole
think
with
it's-
2 stars
It's
going
2 black
around it.
holes.
black holes.
A0620-00 next
Got
to
it.
EJ11118 plus 480.
Got
Obviously.
it. Oh, thank you.
Yeah.
So we have observed it twice, and that helps constrain sort of the behavior in 2 different systems.
And there are other systems where we should be able to see this kind of thing in the Milky Way as well. So
Okay.
future observers and modelers can go out there and see if we can see the same thing.
Cool.
Yeah. All right.
They
so,
can't actually go there.
No.
Why?
Don't
But
Just
speaking
kidding.
about going things, what's
Yep.
the most massive single object
Oh,
sent into low Earth orbit?
Nobody knows.
Somebody knows. Lots of people know.
Ugh.
I know.
Josh knows because he looked it up.
Yes.
Okay, let me
make
guess
the
first
question.
because you probably know.
I don't know.
I think
Oh,
you're good.
okay.
Here's a hint. You're both going to be angry about the answer that I'm going to give you.
Perfect. I love it.
My guess is the Canada arm because people talk about it a lot.
Okay, but the Canada arm was like on a space shuttle,
Right.
and that was launched into low Earth orbit. So is your answer space shuttle?
Space shuttle. With the Canada
Because
arm.
that was going to be my the,
Well, you know
the
what?
configuration
You're not-
specifically that has the Canada
Yeah.
arm.
You're not.
What about the
you're
space
not
shuttle
gonna be angry.
specifically that has Hubble in it? Even.
Oh,
Although I
actually,
don't know
it
how-
wasn't that one.
Oh, okay.
But you are both correct. It is
Yeah!
the space shuttle.
I helped you get there.
Yeah. Congratulations. The most.
Woo!
The
I
most.
actually was sort of thinking that, but then had gone a different direction. But then when you said your thing, I was like, oh, I bet it's like.
yeah. Yeah. Because we tend to think
Space
like
shuttle?
payload, and we think of the space
I know.
shuttle.
I was
as
like,
still,
what are the really big satellites?
Right. Yeah. The most massive space shuttle was STS-117 Atlantis.
Was it one of the ones that had an ISS segment?
I don't know what was in it.
Interesting. I'll have a look. real quick.
122,000 kilograms and change. For comparison, to give you an idea about just how massive that is, the Mir space station
Ooh, yeah.
was barely larger.
Really?
129,000.
Really?
Yeah, so less than 10% bigger than one space shuttle orbiter in mass.
Oh my god.
The Chinese space station currently in orbit is less massive than a space shuttle.
Wow. It's pretty small.
Is that
It's pretty small.
Oh, is it because it's super small or just really lightweight?
It's both.
I mean,
like it was parts
it's
of it were assembled on
96,000
orbit.
kilograms.
They assembled a couple sections on orbit,
Yeah.
I think, and it's pretty lightweight. Yeah.
Yeah.
It was an ISS
Assembly flight.
assembly flight. It had the second starboard truss segment and some solar arrays and stuff.
That was going to be my second guess after
Yeah.
Canadarm.
Makes sense.
What is the most massive interplanetary spacecraft? And your hint for this is I was wrong when I guessed this one.
So, not Cassini?
That's a good guess. Good answer. Yeah, that was my initial thought.
Could you be more specific?
Is it Juno? Is it New Horizons? No. Is it Lucy?
It's not Lucy.
Okay.
Say something. Got
Juno.
dead air here.
Juno.
It was actually the Phobos 1 and Phobos 2
Oh.
Soviet missions to
Wow, I
Mars.
have no idea how big those
I
were.
would have never
They're-
guessed that.
They were 6,220 kilograms each. Cassini, fully loaded, was 5,600 kilograms.
Oh,
so
wow.
about 10% bigger, more massive, I should say. Phobos 1 was an unsuccessful mission. It launched,
was.
it got in the, I don't remember where it was with respect to Mars, but they had we've talked about this actually on a previous episode, what happened to Phobos 1. It was a really embarrassing
Oh, really?
mishap.
Uh-huh.
Was
Yeah.
it one of
There-
those where it was like metric to imperial units?
I mean, it was
an
even more
equivalent.
stupid than that in some ways. So they
no.
sent a command. They designed their system so that a command that was a normal command that you would want to send it differed by only one character from a command that said stop operating.
No.
And so, first, why would you have a command that allows you to say stop operating? Well,
You
they
have
only
to.
had that.
Usually. You usually have to have a kill
Not for
command.
your interplanetary robot,
What if
Really?
It, what if
Yeah.
it
For our
starts?
CubeSat.
because they're in planet Earth orbit.
What if
No.
it starts
We had
to
to have a kill
murder
command.
the aliens?
Yeah.
We had to have a kill command for. Yeah, V'ger should have had a kill command.
Well, there you go.
So-
So in any event,
Star Trek reference.
so that was their first mistake, and the second was they had software that prevented from going up without that missing character or with the extra character or whatever it was. But the computer was broken, and the technician decided, well, what the hell? I'm sure it's fine, and sent it instead of waiting for
That's
the
amazing.
software to be repaired to correct it. Phobos 2, which was the same basic model, did make it to Mars. Did manage to take images of the moon Phobos. Its mission also ended prematurely due to an onboard software error.
Wow.
There's more recently supposed to be a Phobos grunt mission.
I know.
Grunt?
Which I don't.
Phobos.
That's yeah.
Yep.
And the Russians spell it Phobos with an F.
F, yeah.
But that one didn't happen either.
While it may have felt like riding a comet through interstellar space, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel and catch up on old episodes wherever you get your podcasts. Follow us on Twitter
At walk_the_galaxy.
and ask us questions anywhere at wtg@ucf.edu. Our theme music was composed by Richard Rusick. Production assistance is provided by Logan Basinger. Thanks to our listeners in the north of England and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Audrey Martin.
We're the Astroquark, signing off until the next episode of Walkabout the Galaxy.
Bzzz.
Your mom.
Didn't know what to make of that.
Your mom's butt.
The question was
It's the most massive
most
thing.
massive thing. That's a
Usually
classic.
Jim is the one making these.
I know, but Jim wasn't
mom
here.
jokes.
I had to tag in for him.
Okay. 3, 1,
Did you stop?
5.
I need to stop that.
Oh yeah, thanks. 0, 3, 2, 6.